let's look at that, and we will take a very simple, fairly easy approach to that, using rate-limiting steps, or the rate-limiting step to be more precise, and equilibrium, which is also sometimes called rapid equilibrium approach. Okay, let's have. So, enzymatic reactions are about conversion of a substrate to, we have a substrate, we have the product, and we do this with the help of an enzyme. Yeah. So these are the three ingredients we get at minimum. What is happening there? Now, if we assume this to be molecules, so in the special case of enzymes, we have something which is mostly in solution, but it also holds true for other forms. We have also some substrate which is in solution. Yeah, so we're looking at molecules, and of course they have to interact with each other. So if we would come up with the simplest mechanism, and if we believe in these kind of things which are molecules, we would say, okay, we have the substrate which will interact with the enzyme and will form some sort of intermediate here, yeah, in this case, and this will look like something which probably, and that's our typical assumption, where we have something, an enzyme, yeah, where the substrate is in the active site or something like that. Okay, and then we'll get to the product. So that's the simplest things, the simplest mechanism we can probably assume for a non-reversible enzymatic reaction. Okay, so let's come up with a mechanism. Now we have come up with, so we can write down the rate equation, yeah, which will be a simple successive reaction. Okay, A goes to this one, and this goes to B, so this will be second order, the first order. Right. But we have a slight dilemma here, which is very simple, that we cannot really directly observe anything which has to do with the enzyme. The only thing which we probably know about the enzyme is some sort of initial enzyme concentration. Which I will denote as E0, which then gives rise, because everything else in this equation here, everything else is not observable. So we can't see this one, we cannot see this one. So these are non-observables. If you look into the kinetics or the kinetic equations for successive reactions, you need this concentration, otherwise you cannot determine the second rate constant. Not possible. Okay, so we have a dilemma here. So we have to take a different approach. And there are different ways of deriving there, which is historically probably firstly done by Michaelis-Menten, a very complicated approach. And there's Holt and Griggs, there's also Langmuir, Hinchelwood, and others. And I will probably come down to the essence of all that, shortcutting a little bit, but in the end deriving to the same rate equation, to the same form of rate equations, with the minimum fuss, I guess. So what I will do is I will introduce something to circumvent this dilemma, saying, okay, I can't help that. We will not be able to measure these two, whatever happens. So what I will introduce, therefore, is let's say, okay, I will just introduce this to be in equilibrium. That's one of the things I said before. So this is to be in true equilibrium, with the following implication, stating that if these two are in equilibrium at all times, so this means that these are in equilibrium, and that means that I can write down that K at all times will equal this concentration. So I can write down an equilibrium equation for that, which holds true for all times. So this is the concentration of the complex, which I still don't know, multiplied, divided by the concentration of the substrate and the free enzyme. Didn't gain that much by that, firstly, but be with me here, that this will be something we'll be using later, especially we'll be using that we can substitute this AE, assuming that these, of course, are non-zero. I can say that the AE complex actually is at all times equal to K times concentration of A and the concentration of E. So far, so good. So that's something I can actually use throughout. Yeah? I will write these down here as I get further on. So what I have used so far, I haven't used that one, which what I will be using is this equilibrium here from my first assumption. Second assumption I make is that if this is true, then the overall rate will be determined by this step. And that is the actual rate limiting step. Rate limiting. And I denote this for historic reason. I would say this is a small k. So this is the first order, in this case, first order rate constant of the rate limiting step. Still haven't gained that much. Okay, let's look formally. Let's look at rate. That's what I'm interested in. And let's look at rate, which is this. We'll first look, and this is actually the same thing. Well, yes, the same thing. I think we'll look at the consumption of substrate. So we'll look at dA over dt as a function of time, and for formal reasons, this is of course consumption, therefore it must be negative. I will keep this negative sign on the left all times. Still, it is rate, which of course is equal to the production of P here. So the product in this closed mass balance scenario is actually the same, appearing with the same rate as the substrate is of course converted. So far, so good. So, what can I say? I can say the following. I can say, actually, I can say that this will be at least proportional to K times AE. Right? Haven't gained that much. Still don't know about this one. Right? Still don't really know what this is all about. What I can say though is that to really make this equal, so to really make this equal, I can say, okay, this will be some sort of probability. Say, because this is some sort of probability. I say, okay, the probability of the reaction to occur, that this actually converts to the product, and of course, here to the enzyme, again, is proportional to the likelihood, which is K, per time, and of course, and if I look at it in terms of likelihood, I can also say it is likely to be in this, say, the two things which will also be likely. We say, okay, this is proportional to all the enzyme species. So how many of these molecules in proportion to all the molecules of E, all the states of E. Here I actually only have two. Free enzyme, bound enzyme. But what I can say that the probability of a reaction to occur is proportional to this one in proportion to all the enzyme species. And I can write this down. See? I can say, okay, this is proportional to all these enzyme species. Okay, still not finished. Just a second. That means that I have some sort of probability term here, which is the one which is the one which I look at, which is the preferred one, if you want to say, which gives rise to reaction, compared to all states of the enzyme, also the unproductive ones. Okay, and I need one last thing. So this is kind of reaction term here. And I need one more term, and that is something which I introduced early on, saying, okay, this will also be proportional to overall enzyme concentration. Because overall enzyme concentration, the more enzyme I put in, the more drive to the reaction. So this is also proportional to E0. And with that, I'm confident we have all the necessary things, and I will show you this later, as I used this one here, also the, also the tweak, I can tweak on that a little bit later if I need to get the dimensions right, and I say, okay, this is equal. So I have a rate equation, right? No. Okay, because still, dilemma, I have these two which are non-observables. Okay, the dilemma. Let's use this one. We haven't used that one yet, right? Okay, let's use this one a little bit. Just for this one. Let's see. Still the same thing. I have this constant. I have E0. Still nothing changed much. And now I will introduce big K. Saying, okay, we have here on the other, in the denominator, we have K times A times E. Right? And to do the same thing, can't do really much about that one. Okay, leave it in there. So that's E. Actually, if you look closer, there's an E everywhere. And what I get, a little bit of fiddling there again, I have K times E0, and I can actually write it down more clearly. Let's say I have an E, and I have K, I have an A concentration. I have I can multiply out E here. Carefully, because otherwise, in Germany there's a very, very famous program for that, which doesn't really translate that well. Lost in translation, which gives us 1 plus K times A. Closed. Right. So now I can do something which I would normally not do. Because I have this variable here. And typically you're not allowed to cancel them out because you lose a solution. But as we started in first place saying, okay, we can't really fill this with any value anyway, so it's a nuisance, and we can get rid of it that way. And we're happily ever after, because I cancel this out. Yeah? And I do this more drastically here, really wipe it out, just to make my point clear. And I need a little bit more space for one final clue here. Yeah? Saying, okay, I have now something, a rate equation here, where there are only observables. Yeah? Observables in there, yeah? Or parameters which I can determine experimentally. Yeah? So I have an initial enzyme concentration, I have concentration of A, I have two constants here, and that's about it. Which I can do if I want. And then we get something where we have some sort of K. Yeah, we still have E0 here. And I get a K times A. And I also get K here. Yeah. Bracket. I get to compensate that, I get K to the power of -1 plus concentration of A. Right? So again, not losing anything, it's still in there, you can cancel this out very nicely. And then, just for the argument's sake, okay, denote something where I say, okay, I have some Kn, which is equal to K to the power of -1. And then do the other thing which is typically done, I say, okay, I have some sort of V, or I would rather say not V, because this is a German error, actually, it's German mistake, which is typically conducted as you would say, okay, this is a rate, a limiting rate, which is actually my small k times my initial enzyme concentration, which is typically done. Then you can state, and that is something which you can do, but you don't have to, then you get to a very familiar form of this equation, which is limiting rate times concentration of A divided by Kn plus concentration of A. Which is hopefully convincing the Michaelis-Menten form of this equation. Does not need to be done, because actually we have finished here. So this is my true rate equation. Yeah? This is my true rate equation in the sense that this describes dA dt fully, and of course also d dt and the occurrence of t as I mentioned in the beginning, and which is actually the same thing. Yeah? So actually, in terms of rate, we finished here. And I find this a rather convincing shortcut approach to all these kind of rate equations. And they will all look the same. And there's some examples in the lecture as well. But you will find that this cancelling out of E can be done for all these kind of equations. At least I have not found one for which this doesn't apply, because in the end you will always refer back to some enzyme concentration here, yeah, related to anything else by equilibrium, and thereby you get something where you have a rate constant, you have the initial enzyme concentration, you have something where you have a concentration, a driver concentration, yeah, which in this case, of course, is the substrate, which is reasonable enough, and then this is the driving rate. Yeah, so everything here, this gets faster, the higher concentration A, and if actually this one also gets bigger, the higher concentration A, but of course diminishes the rate in terms of the rate gets lower the higher this term is. So this is the absorption equation. And this concludes my short input in terms of rate equations for catalytic reactions based on rate limiting step 1, an equilibrium demonstrated on this minimum example here, deriving the Michaelis-Menten type of equation in, let's say, the minimum number of steps. Thank you very much.